Доброе утро. Я буду рассказывать про множество Mandelbrota и про динамика метода Ньютона. Но, наверное, вы все лучше будете понимать, если я на английском говорю. So that's what I will do. Welcome again. I briefly announced my talk the other day already, so I have to warn you, about half of this talk will be completely useless. And then for the other half we have to see, and in the end you have to decide whether it makes any sense to ask what's useful and what's not. I believe the distinction should not be made. Can you all hear me?
Yeah.
Okay, very good. Next thing. So let's start. I want to start where you are. Do you all know complex numbers?
Yes.
Okay. So, and generally speaking, if you have questions, please interrupt me, please ask, because I want you to understand what I'm saying. And it's usually easiest if you ask a quick question, and then life is much easier than if you decide it's too complicated. Chances are it's not, you just have to ask a question. Okay, so let me start. The main character, or one of the main characters of this presentation is already on the board. That's the Mandelbrot set. And I asked the other day, many of you had seen that before, I guess. So this is the most useless set in mathematics. If you look at some versions of Guinness Book of Records, it's there as the most complicated set ever studied in mathematics. I'm not sure whether that's true, and I think that's a useless question what record there is. But it is a complicated set, and people have tried to study this with quite some energy and effort. So, what is the definition of the Mandelbrot set? Let me give you one definition. Am I writing large enough for everybody? Again, you complain if not. It's the set of all the Mandelbrot sets of all C in the complex plane, so that the sequence 0 mapping to 0 squared plus C, which is C, mapping to C squared plus C, mapping to C squared plus C, squared plus C, and so on, is bounded. So you start with 0, and then what you do is you square the number. You have a particular number C in the complex plane. And for that number, you start with 0, square it, add C, then you get C, obviously. You square it again, add C. You square the whole thing again, add C, and so on. And then the sequence may either be bounded or not. If it is bounded, the point C belongs to the Mandelbrot set. If it is unbounded, it does not. And then here you see in black the set. Black are the points for which the sequence is bounded. And the colored points, for them the sequence is unbounded. And the color says something about if it's unbounded, that will go to infinity, just how fast it goes to infinity. More precisely, the colors say how many iteration steps are required until the sequence reaches absolute value, say 1,000,000. So far out in blue, it takes just a few iterations, and then yellow takes longer, red and the other colors take longer and longer and longer until you get close, get to 1,000,000 after that. Well, then just some big number. Now let's do that together. Well, let me draw the set for a moment ahead of time. So it's something like this here. And we can try, just to get the idea, to start simple, we can try to do this by ourselves. So the simplest point is C equal to 0. That's about here. What is the sequence doing in this case? The definition is here. You take 0, you square, you add C, you square, you add C, for C equal to 0. So what do you get? 0 all the time. Is that bounded?
Yes.
So is the point 0 in the Mandelbrot set or not?
Yes.
Okay, so here we have 1 point in the Mandelbrot set. And one of the things you learn, never trust the computer, it's blank anyway. Do it by yourself. And we just proved that the point 0 is in the Mandelbrot set. Questions? Vопросы? Question, Fragen? Okay, so let's try some other point. How about the point -1? C equals -1. What happens? Bounded. So what's the sequence that we get?
1, then 0, 1 again.
It alternates between 0 and 1. So hold on, actually this we get -1 here. 0 squared plus is -1. The -1 squared is 1 plus -1 is 0, and then we get -1. It alternates between 0 and -1. So it's bounded, and that's the point here. So this is c equal to 0, c equal to 1, and -1. How about -2? Yes? -2 and then 2. So this doesn't alternate, it becomes fixed. So you have -2, then this is 4 minus 2 is 2 again, squared is 4 minus 2 is 2, then it stabilizes at 2. So that is the very end point here. Well, let's check +1 for instance.
It's unbounded.
It's unbounded. What does it do?
Oh, because it grows at least 1.
Okay, so 0 squared you get 1. 1 squared plus 1 is 2. 2 squared plus 1 is 5. 5 squared plus 1 is 26. And 26 is already pretty unbounded. And from there on you see how it goes on. Okay, so c equal to 1 is not in the Mandelbrot set. Okay, so how about one last question? I, the complex unit. Let's write this down. Just to make sure, I squared is?
-1.
Thank you. I squared is -1. So I maps to I squared is -1 plus I. So I get -1 plus I. And now we have to square that thing.
But I. 2i.
The square of this is 2i. This is I or it's -2i. So this goes to I again. And then it cycles. Okay, so the point I sits exactly here. So this is bounded, and then you can see so I think it will be coming here. So can you see the mouse? So 0 is at the origin here. You see the mouse, there's 0. This is -1. This end point, the very end is -2. The end at the far right, this is 1/4. This point here is I. This thing is -3/4 where they touch, -5/4, and so on. So some of the points you can calculate exactly. But I hope you have an idea now what the Mandelbrot set is. And so a few things that one can check, that you can check for yourselves. this thing here is a round circle. It's the only round circle in the Mandelbrot set. So this is the disk with the radius 1/4 around the point -1. So there you see a perfect circle. Here, this is called the main cardioid. You can also give a formula for that, and for some of the others, there are more complicated formulas, and then Galois theory gets in the way. Okay, so that's the definition. And so far, I think it's completely useless. So why do we discuss this set? Of course, it was discovered, and once you discover, it's a very simple definition, and you get a very complicated object. It's already quite interesting. But there's a more systematic reason why this is an interesting set. Let's do dynamics of quadratic polynomials. That is a theory that was started around 1905 or so, in some part even earlier, but the fundamental results due to Fatou and Julia are from the beginning of the 20th century. So we have polynomial p index c of z equals z squared plus c. I want to tell you a few things without proving it. Once, the dynamics of degree 1 polynomials is boring. I could tell you why, but it's still boring, so we ignore that. So the next interesting non-trivial thing is if you look at quadratic polynomials and do the dynamics, which means you iterate these polynomials, apply them over and over again. And that is not boring. And you can take different polynomials, can be the same dynamical system in different coordinate systems. So if you choose appropriate coordinates, you can write every quadratic polynomial in this form. I will not make this precise for now unless somebody asks me, but the message is, this is, if you want to know anything about quadratic polynomials, you could write them as az squared plus bz plus c. By translating the origins of the coordinate system, we can make b equal to 0. And by scaling the coordinate system, we can make a equal to 1, and we get that without losing anything. So if you do dynamics of polynomials, you look at the simplest non-trivial case, which is quadratic polynomials, and you can write them all like this. So this is a natural thing to do. It may be useless, but at least it's natural. And again, you can define K, the filled in Julia set, depending on the parameter C, is the set of all points Z in the complex plane, so that the orbit of Z is bounded under iteration of the polynomial PC. This is a dynamical system. The Mandelbrot set is not a dynamical system. This is a dynamical system. You have a map. It's a discrete dynamical system. You iterate the map on the complex plane, and you ask for every point, what will happen to this point if you keep iterating your polynomial? And then the most fundamental question is, the orbit could go off to infinity or it could not. Again, let's look at a few examples. K0. If c equals to 0, the polynomial is simply z squared. Which points converge to infinity under iterations which stay bounded? So the picture, just a closed unit disk of radius 1. I don't have a picture on the computer, I could make one, but I hope you see that if the point z is an absolute value 1 or less, then under squaring the absolute value will remain 1 or less. If it's less than 1, it converges to 0. If it's 1, then it stays where it is. While if the absolute value is greater than 1, you just square the absolute values and it goes off to infinity. Right? So this is one interesting set. Let me give you another, k for the parameter -2 at the very end. I could let that to you to figure it out, but let me just give you the answer. It is the interval between -2 and 2. You can check that for yourself. I may have some other pictures of Julia sets. What else could come up? Let me see what I have in the offering here. I have more. So where do I have all my Mandelbrot set pictures? Oh, you don't see it anyway for some reason. Well, I have no picture yet anyway, but I'll find you some. Is it coming? No, what's happening here? No signal. That cannot be true. There is a signal. Should I just disconnect and connect it again?
Let's try.
My computer noticed this immediately. But now it doesn't notice the beamer anymore, the projector. So why are you not, it's not responding at all. Okay, now it's thinking it has a beamer for some reason. And when I put it in, something is very funny here. So the computer, now it's on and it's doing what, is it? Yes. It was working so nicely. See, now it's crashing here. I cannot use the mouse anymore. Okay, hey friends, I think I'll restart the computer and hope that things will get better. So this takes a moment. Okay, so I will show you some more pictures in a moment once the computer is restarted. And so what will I tell you? So these Julia sets can be very, very complicated. In particular, let me try to convince you. So these are all Julia sets. Let me draw some other Julia sets. Now what they look like. For instance, k equal to -1 looks, it's called the basilica for some funny reason. Looks like a collection of topological disks attached to each other. Yes? Of k.
The definition itself.
Okay, so what do we have? We have points. I have a fixed k, so k -1. Parameter c equals -1. That means we look at the map, z maps to z squared minus 1. And for every z, we iterate the polynomial and see whether the point goes to infinity or not. If the orbit is bounded, it belongs to kc. If it's unbounded, it does not.
Is there some movement that shows how the picture varies as the sea varies?
Oh yes, there are lots of movies all over the place. I don't have one here, but there are many so-called experts who claim to give a talk about mathematics and just show pictures. I want to give motivating pictures, but then I want to do mathematics. After all, so far this is all very useless. Let's see what happens. Now it did not, but it could be that my computer was to blame. No, it is. So the situation is that as soon as I plug this in, the computer stalls. But that was.
I see.
It worked before, and now I restarted the computer. So we have this. Maybe it was confused, or I was. So at the worst, I would have to ask you to sit closer together, and or maybe we transfer the files over there.
Just
If we have a memory stick. Okay, so I tried to repeat the definition here while the technical things are trying to work themselves out. No, they're not. I don't know what happens here. So the definition is the following. We have the map z squared minus 1. Now we look at every point in the complex plane. What does it do? Does it jump? Where does it go? And we check the 0 goes to -1, goes to 0, goes to -1. So 0 and -1 are both in K. -2 is not, because -2 squared is 4 minus 1 is 3. 3 squared minus 1 is 8, and so on. Then it goes to infinity. Hold on. It's now doing something, just this very second.
испугался.
So now it is me remembering it saw the thread that you were coming, and so have we. So now at least it cooperates. So the computer is making progress. It's finding the displays. I think now it's a problem of the beamer, of the projector. Because the computer notices that there is a device.
There's some problem.
That will probably take a while now. Okay, so then you work this out, and if that doesn't work, then attach the other one, we work with that one. Okay, is the explanation okay? Okay, so there are some, so we're getting interrupted. That's a bit unfortunate, it takes time and it's difficult to understand then. These are cases when the Julia said they look very different here, but they're all one piece. There are also cases when the Julia said it's not one piece. For instance, if I take, let me go over to the other side. As long as we have real quadratics, we can always draw the graph. So we have x squared minus minus 5 or x squared plus 1 we had. So the graph is such a thing here. And we have, do we have a fixed point? Oh, this looks good. I don't know what happened. You just restarted the projector?
Yes.
Okay, so that was it. So here is a picture of a Julia set. This looks more complicated now. It's still connected. The Julia set is black again. It is connected. You may not see it, but it's a very fine connection between all the spots. That's a connected set. Here is an example of a Julia set which is not connected. Remember, it's only the black. The colors go to infinity at different speeds, and the black is somewhere hidden in all the components. Every component of the Julia set is a single point. So no two points are connected in the Julia set now. It's just quadratic polynomial, it's just a different one. Here's another one. Again, disconnected. It's just like a dust of a cloud dust of points. Here we have one which is connected again. Very deep studies have been made about this particular picture. I will not go into this. Okay, you see different pictures here. They can all look very different. And now you can ask the simplest question, are they connected or are they not connected? It could be either dust, you've seen some Cantor dust, or it could be a connected piece. So let me define the set of all parameters C for which the Julia set is connected. That is a reasonable definition. Now we have every point in the complex plane is just a parameter for this polynomial z squared plus c. And you ask for this parameter only one question: is the corresponding Julia set connected or is it not? Okay? And you want to know what the answer is. Let me show a picture of all the parameters C for which the Julia set is connected. Do you understand the question? So here is the picture. So that's the same thing again. The Mandelbrot set not only has an easy definition with which you can calculate it, it has a more meaningful definition. It's the sort of a table of contents of quadratic polynomials, quadratic Julia sets, and describes which of them have connected Julia sets or not. So if you want to understand the dynamics of quadratic polynomials, then the Mandelbrot set tells you what which Julia sets are connected, which ones are not. So there's at least some meaning in it now. Let me tell you why, just to give you one theorem. This is a Fatou from 1906. If you have a polynomial and you want to find out whether the polynomial has a connected Julia set or not, definition of Julia set is clear. You want to find out whether the Julia set is connected or not. Then you look at all the points where the derivative of the polynomial vanishes. These are critical points. And since we have quadratic polynomials, there is at least one critical point. You look at all of them and you look only what they do under iteration. If at least one of the critical points goes to infinity, the Julia set is disconnected. And if all the critical points have bounded orbits, then the Julia set is connected. It's not very hard to prove. I will not do it here though. So let's look at the polynomial z squared plus c. It's a polynomial in z. So what's the derivative? 2z. 2z. And what are the critical points? 0. It has one critical point that's 0. So the theorem that I just mentioned says that the Julia set of z squared plus c is connected if and only if the orbit of 0 stays bounded. And that's the definition of the Mandelbrot set. So it's the same thing after all. Well, far. So then let me tell you one more useless fact about the Mandelbrot set before we go on to Newton's method. So those of us who work on the Mandelbrot set pretty much know what it looks like. Let me give you a topological way of drawing the Mandelbrot set without knowing anything. So this will be the Mandelbrot set. We have a circle. And now we look at the numbers 2 to the n minus 1. I cannot explain everything, but let's do that for now. So n equals to 1. So n, what is it? If n is 1, then 2 to the n minus 1 is 1. So we look at the point, actually, more precisely, we look at the points numerator k over 2 to the n minus 1. So 1 is boring, 2 is interesting, 2 to the n minus 1 is 3. So we look at 1/3 and 2/3 here on the boundary. Here's 0, there is 1/3, there is 2/3. And this is again 3/3 is 1. Okay? So we have 2 points on the circle and we connect them any way you like. And now we declare that this connection is just a point. So we squeeze the disk, we squeeze it at this point so that there's 1 point of connection left. Okay? So we have 1 disk here, 1 disk there, and they're touching at 1 point. You see that? So that in the Mandelbrot set, so we have something like this thing here. Already looks a bit like the Mandelbrot set with the 2 big disks. From the point of view of topology, it's the same whether we draw a disk or something like that. That makes no difference. Okay? So now for n equal to 3, 2 to the n minus 1 is 7. So we have 1/7, 2/7, 3, 4, 5, 6/7. Again, we squeeze these to a point, that to a point, and that to a point. So we get another disk here, and another disk here, and another disk somewhere there. You see that there's a big disk which is touching 2 other disks at this point and at that point, and then there's a string of 2 further disks here which are touching at 1 point, because all these arcs are just 1 point. So that's that. See that? And then for 4 we get 15. So 1 and 2/15, 3 and 4/15, 5/15 is a third already, 6, 7, 8, 9. Now we cannot connect these two because there's only 1 point which separates them. So I have to connect here and there because you cannot cross. And then again we get these 2. And in this picture that means we get a ball here and 1 there and 1 here and 1 here. And this is in between. Looks a bit like that. And you keep doing this. And you go to the limit. And if the limit is n tends to infinity, you get a topological set here, which is homeomorphic to the Mandelbrot set. Actually, that's a conjecture. You understand what I'm doing here? So that is a very simple model for the Mandelbrot set, except we don't know it's true. There's lots of evidence that it is true, but this is a nice topological space, it's locally connected, whatever that means. If it was topologically the same as the Mandelbrot set, then the Mandelbrot set would be locally connected. That is a big conjecture. If you prove that this is the Mandelbrot set, you'll be very famous. People have gotten Fields medals for just partial in this direction. Many people have worked on it, so this is an open question. There you have a complete and simple definition. Here you have a complete and simple definition. Just show that the two things are the same from the point of view of topology. Combinatorially speaking, they are the same. Topologically, it's not so clear. So, but mathematics is full of open questions, and even though some of the results are old, some of this is very recent work. Isn't this a beautiful blue? I don't know what to say. Okay, technology is always full of surprises, like mathematics. Okay, I wanted to change topics. I'm not making much progress, unfortunately, with the computer always annoying me like this. Some experts can help me with the machine. Okay, I wanted, so let's change gears. I hope somebody will come and take care of this machine. Can I unplug it again? I never know what happens then. My computer notices this. Okay, now we have the same story again as before. Give it a time. Now my computer is waiting and thinking again.
Try to turn off power save mode in your computer and sleep mode.
Yeah, I could. So that worked last time. Can I ask you to stay here and hold the hands of this machine? Okay, I put this thing back on again. Still, now it's stalled and waiting for something to happen. Okay, so I want to move on, even though this is a very this is stalled. So let me change gears. Any questions so far? Then let's do something useful. Let's try to find roots of equations such as polynomials. So we had this here before. Newton's method looks like the following. You have a graph of some function which is smooth. You want to find the positions of the roots. So is this guy, okay, the computer is recognizing this. And Newton's method consists in taking a random starting point like so, taking the value, drawing the graph, the tangent to the graph, and see where the tangent intersects the real line. Here we have another approximation. Let's see what happens. Here we draw another tangent, which looks like so. We have a better approximation, and the next tangent is already here, and then it's hard to distinguish, and we get very close to the root. So my computer says things should be okay. Okay, so that is Newton's method, and if you just draw the little, calculate the function, if f is the graph, then fx maps to x minus f of x divided by f prime of x. Okay, the computer's in favor. Thank you. Okay, so that's the mapping for real values. This before, I guess. And the current wisdom is if you're near a simple root, then the number of valid digits will double in every step. So if you have one valid decimal or binary digit at some point, after the next iteration you have 2, then 4, then 8, and 16, and more will not be feasible with your computer. So locally near a root, this will converge very quickly. But current wisdom also says that globally it's very difficult to predict what happens. History goes as follows. Cayley, you may have heard of the mathematician Cayley, like the Cayley-Hamilton theorem or Cayley quaternions. Cayley published a paper in 1876 in which he proved the following. Well, first of all, you should realize that this works just the same for complex numbers. So if f is a polynomial, then this thing is a rational mapping. You're doing iteration of a rational function, right? Which is something that fits well into the context of complex dynamics. I have to entertain my computer here so nobody falls asleep, like I have to entertain my students so nobody falls asleep. Double purpose. So we iterate a rational function for Newton's method. We do this in the complex, and Cayley proved the following. If you have a quadratic polynomial, here are the two roots of the quadratic polynomial. Then you draw the bisecting line in the complex plane like so, and all the points on this side under iteration of Newton's method will converge to this root, and everybody on the other side will converge to that root. So there's a very simple description which under the iteration, which point, if you iterate Newton's method, which points will go to the one or to the other root. Nothing could be simpler. Okay? So he proved that, and he said an analogous result for cubic polynomials will be published in due course, in the near future. Unfortunately, that paper never got published. And the reason why it never got published is this. That is the dynamical plane of a cubic polynomial. You have a cubic polynomial in the complex plane. We always work on the complex plane. I have to say this. Real mathematics is difficult. Complex mathematics is beautiful. Always do it in the complex. So in the complex plane, you have a root somewhere in the center of the red domain. Here, there's a root which I call red, there's a root which I call blue, and there is one which I call green. And as you iterate Newton's method in the complex plane, you can see which starting point converges to which of the three roots. And you see the picture is much more complicated than the picture of the quadratic case. So Cayley had no computer, and without computer he had no chance to understand what was going on. This is very complicated. Let me show you some other. So where did I have? Let me show you another picture. Or is that the same? That is the same. Okay, they look somewhat similar. So you see the idea. So that's pretty much the picture that I also showed the other day. However, something very bad may happen. Not only converge most of the points to the three roots, if you look very carefully, you see some black spots here. You see that? That is not dirt. There are black points which do not converge to any of the roots. So that's really bad for Newton's method. So let me have a blow up here. That is, yes, if you look at this region here and have a blow up, you get this. So the set of black points, that's the set of bad points for Newton's method, they have a very funny structure. And now you can ask, what is this black set? How can you explain it? So you understand that this is a useful question. Newton's method finding roots is a useful question, and the black points are the bad part and the good thing, so you have to understand what they're doing. Show you some other picture. Let me see what happens here. Okay. Do you recognize the similarity? Do you see that this is the same set? You see that? So this here on the left is the bad points for Newton's method of a cubic polynomial, which is useful. This here is the Julia set of a quadratic polynomial. Quadratic. So it's exactly the kind of thing that we discussed earlier. So, in order to understand the useless things, you have to understand the useful things, you have to understand the useless things in a very natural way. All these points, and it can show you lots and lots of more examples, all these points which are bad for Newton's method are coming from quadratic polynomials. So let me see whether I have another one here. That is another complex polynomial, cubic polynomial. You have three roots, red, blue, green again, and again there is some black in the middle. And let me give you a blow up of this. This here on the right, this is the blow up of that region there. I hope you see that. And now the next thing will not come as a surprise to you anymore. If we show this, that is the same set up to topology or even better, and that is the Julia set of a quadratic polynomial. Okay, so I'm not finished with the pictures. Let me draw something different. Let me draw a table of contents of all cubic polynomials. After all, one of the most famous mathematicians of the 20th century had asked a question on this, Stephen Smale. He was mentioned in some of the presentations in earlier days in the context of the Poincaré conjecture. Stephen Smale saw these things in the 70s or 80s of last century. It was discovered that you could have open set of black points. And he asked, for which polynomials can you have open sets of black points? So let's look at the space of cubic polynomials. This is the parameter space. It's a parameter space, like here we have quadratic polynomials, we have Julia sets for every polynomial, and the Mandelbrot is the parameter space. Every point in M corresponds to a different Julia set. Remember? Here we do the same thing. Every cubic polynomial has its Newton dynamics that we saw before. And now this is the space of cubic polynomials. Every point is a different cubic polynomial. And again, this story, we discussed the critical point here. There's again a story of a critical point. To make life easier, let me say it as follows. If we have three roots of a cubic polynomial, we look at the center of gravity, which is perhaps here. Theorem. If there exists a bad set of starting points, black set, with interior, then this center of gravity of the roots will be part of it. So in order to find out whether a particular cubic polynomial has an open set of black points, which is bad, you only have to look at this particular center of gravity. So for every cubic polynomial, we look at this point and see what it does under iteration of the Newton map. If it goes to the red root, then we color the polynomial red in the Newton method. If it goes to the green root, we color it green and blue the same. So all those which have colors, all those polynomials do not have open sets of bad points. But some do. I have made a little blow up of this region here. There's another one, and you see a black spot there already. So the black spots here describe exactly those polynomials for which there are bad sets. Okay? And you agree that in order to understand which Newton polynomials are bad, so to answer Stephen Smale's question, we have to understand the set of black points. Right? So let me show you a blow up of the set of black points. And that's this. I think you're no longer surprised to see this. The thing on the left is a blow up of that guy here. And we can move on. I have a blow up again of this little black spot there. And what happens is that. Okay. I hope you guys are no longer surprised. And of course that's a theorem. That set, all these black sets are homeomorphic copies of the Mandelbrot set. If you don't know what homeomorphic means, it's the same from a continuous point of view. That's a famous theorem. Another theorem is that all the black points for the cubic space are understood in terms of countably many little Mandelbrot sets. So in order to understand the useful thing of Newton dynamics, you have to look at the useless stuff of iteration of quadratic polynomials. The Newton dynamics is relatively easy to describe for cubic polynomials, except for the parts of the Mandelbrot set. All the difficulties of Newton's method for cubics are encoded in the Mandelbrot set. So all the open questions that we still have about the dynamics of Newton's method are in fact open questions about the Mandelbrot set. And now you could try to move on. That's the situation for cubic polynomials, but beyond cubic polynomials. Stephen's mail asked for arbitrary. After cubic polynomials we can still relatively easy solve. It's just degree 3. So what about degree 7 or degree 100? How can we understand them? So let's look at Newton's method of a polynomial of degree 7. I have such pictures too. Here, that is a polynomial of degree 7. Now you have 7 different roots in 7 different colors. There is gray, there is brown, there is red, there is green, there is yellow, there is blue, and there is purple. 7 different roots, 7 different colors. And again, every point in the complex plane is colored according to which of the 7 roots they converge to under the iteration of Newton's method. Try to understand that. Now good old Cayley again of 150 years ago. He would have no chance to say, well, a similar description I will publish soon. He will not. He does not, because there is no chance. But we are making progress on understanding these sets. But you see, it's not quite so simple. Let me show you one more picture for real. I hope I have. No, I do not. I have to find a real one for you. Here. So that is a polynomial of degree, let's count. How many roots do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Degree 11. 11 different roots. And so that all the roots are real. So you would think real numbers are easier than complex. All the roots are real, so let's count the roots on the reals. And you will discover that here there are 4 real roots very close to each other. So in the graph it would just look something like, and these things are hard to distinguish. You could overlook them. In the reals, bisecting, you might not find it. However, if you look at the colors in the complex here, you see that the leftmost of the 4 has a big blue domain, the next one has a big yellow domain, then there's a big gray and a big purple. So in the complex, they're very easy to distinguish. So if you want to find the real roots, you better look in the complex. Remember, real mathematics is difficult. The complex methods are often better. Okay, so what questions are there? Smale still asks the question, can you describe in all degrees those polynomials which have extra sets of points that converge to no root? Give a classification of those. I'm very proud of my students. All of us professors are very proud of our students. A current graduate student of mine, from Belarus actually, he solved that question. he not only classified all the Newton methods of polynomials which have extra cycles, he classified all the possibilities that could happen. This is all the pictures you've seen, degree 7, degree 11, and so on. All the possibilities that one can have. In terms of graph theory, one can describe exactly which possibilities can or cannot arise, and where the extra cycles are coming from. So these were deep questions by deep people, but it's always nice to know that people like us can solve these things. It's not just those somewhere in the famous universities or whatever. And this is a message I want to send to you too. We can make progress in mathematics. Whether it's a current student of mine that is just 3 years older than you, or you guys in 3 years or less, there are lots of open questions that can be answered, and this was an open question that now is being answered by Zhenya Mikulic from Belarus, currently in Bremen. I will not give you the answer. It looks the graphs are complicated, but still all the different possibilities can be classified. So let me show you another favorite picture of mine. Remember, this is the cubic polynomial here on the right, degree 7, and I've drawn the same picture on the sphere. This here is the sphere. Who of you has heard of the Riemann sphere? You will, before too long. So, for practical purposes, that is just a complex plane with one point out at infinity. And you have the complex plane is wrapped around so that it meets again at infinity, at the point infinity. And here you can see infinity, you can touch infinity. It's not so far away as you thought. So another way of thinking about it is stereographic projection. That's something you probably know. You have the plane here, you have the sphere, there's the North Pole, and then you project any point on the sphere from the North Pole through the sphere onto the plane. Right? And that projects the sphere without the North Pole onto the plane. Except the North Pole, points near the North Pole go very far away, and the North Pole itself is the point at infinity. Okay? So here you see it, and here you can see infinity very nearby. Okay, now let's remember Newton's method. After all, the goal is to find roots of polynomials. So you want to find, you're given a polynomial, f, you want to find all the roots. Well, there are high-tech methods, and the professionals tell us, don't use Newton's method, because it's unpredictable. You never know what happens. You could by chance land near a critical point, and then the graph is almost horizontal. You go very far to infinity. In other words, you would land at the pole of this map, go to infinity, or near the pole, then you're near infinity, and then you lose control. So they have methods that they can understand better, even though Newton's method is beautiful and simple and fast. And that's something that I have been doing over the last few years. And since we're talking about current mathematics, I would like to tell you something about current results that just yesterday I was working on writing it up. I'm convinced that Newton's method is much more useful than what the numerical analysis people really think. And it may be faster than their methods, only they don't believe it. So one thing is, you see that all the colors, let me call basin, the basin of the yellow root are all the yellow points here. The basin of the red root are all the red points. So sort of all points converging to this root under iteration. And one theorem shows that every basin can be connected to infinity, or every root can be connected to infinity through its basin. You would not have thought this like Cayley, just with your bare hands, but since we had computers available, we could make conjectures. And that was discovered some 20 years ago, maybe 30 years ago, and subsequently proved every root can be connected to infinity through its own basin. Now let me go back to the complex plane. That already helps us to understand the dynamics of Newton's method. You have a polynomial, and usually it's quite easy to give a bound on the positions of the roots. So suppose you have a disk which contains all the roots. Let me draw this somewhere. So here is a disk which contains all the roots. We don't know where they are. But we know that we can connect them all to infinity in their own basin. So let me use some colors. For instance, well, this is not white, it's some other color like pink. This is blue. May go to infinity in two different directions. And then there's some green here, which again connects to infinity. So if we take a big circle, like so, we necessarily have to intersect all the basins. So we may not know where in the disk the roots are, but on this circle we can intersect all the roots. So we don't look for the roots where they are, but we look for them near on the circle around, in the complex plane. And remember the picture with the reals. They could be very close by here, you don't find them. But on the circle around them, they're very easy to find. See that?
Sorry, so there is no black areas in the huge circle?
There is. There still is. You have to... In fact, they're everywhere dense. So in every boundary, every point on the boundary, if there is black, then any boundary point here, in any neighborhood of the boundary, has black points. So the blacks are dense in the boundary. But so you find there may be black points, we cannot avoid that. But we want to find the others. So we have on this circle, we know there may be black here, whatever, we don't know. But at least we can find the other points too. And the next thing is, a theorem says that the channels to infinity have a certain thickness. They're not too thin, but they are, you can measure what thickness should mean and can prove the lower bound for how thick they are. So what you have to do is have enough points here on the circle, makes this precise, and then when there are enough points on the circle, then you can be sure that every basin will be intersected, so every root will be found, even though there may be lots of black points. So the theorem goes as follows. It is about 10 years, now we get to fresh results. It's 10 years old. HSS. H is my former PhD advisor, John Hubbard. That is colleague Scott Sutherland, that's myself. There exists for every degree d, there exists d times log d squared times 1.1 points. I don't want to write everything, I have to stop in a few minutes. D points, like here on a circle, on several circles, from which we are sure they will find all the basins of all the roots. So if we want to find, if d is the degree, if you want to find d different roots, we need at least d points. Well, there could be all the black points that we meet, so that may be difficult. Log d, so we have to have a few more spare points in reserve in case something happens to the others. So factor 1.1, 10% isn't too bad. And then log d also is not very big, even log d squared. So if you have just a few more points than d, then you can be sure that all these points will intersect all the basins, you will find all the roots. Let me remind my computer it should not go to sleep yet. So that was 2001. Here's a newer theorem by Bela Bolobash, Malte Lackmann and myself from 2010. We proved that in spring. You can get d times log d squared points. So not log d, but log d is still enough. Just barely more. Log d is really a very small number. So people joke that log d goes to infinity as d goes to infinity. But it's never been seen to go to infinity. It's never been observed. Because it's so slow, nobody will ever see it goes to infinity. So, even now, you can make some more progress that this, for a quite practical problem, you don't need many more than this number of points to be sure to find all the roots, even if there are black points. And what I'm currently working on, the number of iterations, how long does it take? After all, the experts say Newton is too slow, you never know what happens. Is at most d squared times log d to the fourth power or so, times a constant, normally. So there are some bad cases. And so this is what I'm currently working on. I need a new graduate student to work on this. That means that this may be even the fastest method available for finding roots of polynomials. And that's a nice conclusion of the theory. Newton started the subject hundreds of years ago. He started analysis. He developed a method which was in practical use, and the theory said, don't use it because it's unpredictable. And now it turns out it is predictable. Once you have computer methods available, once you have methods from complex dynamics, from complex analysis, from hyperbolic geometry available, it connects with many different areas of mathematics. And all of a sudden it becomes a quite useful topic. And it's being used. So I think even though the computer was stopping me, or the projector, I'm being asked to stop. I want to show you one last picture. Just to show you that there's always more work to do. This is not a polynomial. It has infinitely many roots. But you can move on once you understand Newton's method for polynomials, which means finitely many roots. You can go on to functions which have infinitely many roots. And there's a very famous function with infinitely many roots, and that is the Riemann-Zeta function. Who of you has heard of the Riemann-Zeta function? A few of you. So there's the famous, I will not describe it, it's an entirely topic in its own right. But that is a famous function that came out in number theory. And that has implications. The zeta function implies how well the primes are distributed. And if we know something about the location of the zeros of the zeta function, it has consequences on the roots of the primes and how they're located. So this is a very, very powerful function. And one of the Millennium Clay problems worth $1 million is to prove that all the zeros of the zeta function are at real part 1/2, so on a vertical line. Okay, how do you find, this is a complex differentiable function, how do you find roots of complex differentiable functions? Well, you run Newton's method, and that's the picture here. So, here you see all the roots aligned. These are just little spots, you may not see them so easily. They're all perfectly aligned on the axis with real part 1/2. So what more could you ask for? So that's the picture for the zeta function, Newton's method. And again, the computer tells you that the structure is very beautiful. And now it needs somebody, we've seen the pictures, now it needs somebody to actually work on it and make this into beautiful theorems. So that is the conclusion of my talk. There is a lot of open questions still to be done, interesting questions, theorems that just wait to be proved. Several of them I showed to you. Even though many of the topics are very old and very classical, there's still a lot of work for us to do. And of course, that's an invitation. If anybody of you is interested, enjoying this work. I'm very happy to work with strong people, either in Bremen at Jakobs University or in cooperation. Some of you know the University of Higher Economics in Moscow. My colleague Vladlen Timorin is working on similar things. So I wanted to conclude with an invitation for active participation in mathematics. Thank you for your attention.